Okay, I'll give you a 2-loop example now. I had given as an exercise, but I think it will be good to have one example at least. So let's look at this Feynman diagram. This is again in 5-4 theory. So what we are looking at is G tilde P1 P2. Okay, so I have momenta P1 and momenta P2. Okay, so everything is going into the diagram, and I want to write down the expression for it. So if I use my Feynman rules that we have derived earlier in the previous, here. So I should include such a factor for each external propagator. So let me do that. So I should have I over P1 square minus m square plus I epsilon times I over P2 square minus m square plus I epsilon. Then I should have a overall momentum conserving delta function. So I have 2 pi to the 4 delta 4 P1 plus P2, because both are ingoing. So I have a P1 plus P2. Okay, this says that the sum of incoming momentum is 0. Good. Then we also know that I will have, of course, other propagators, but I will have some undetermined loop momenta which will be integrated over. So let's call this one L1. Okay. So P1 comes in, L1 goes out, but these two are still not fully determined by the momentum conservation that happens at this vertex. Okay. Remember, before we arrived at these Feynman rules, we had already seen here somewhere that at each vertex you should have here at each vertex we should include a delta function which imposes conservation of momentum at that vertex, at each vertex. Okay. So that is still there, but now we don't write that explicitly, but rather when we do the momentum assignment, we take care of it. So here you see that I have one momentum incoming and 3 going out, and clearly using just momentum conservation I cannot fix all the 3. So I will be left with, so I will, let's say I label this as L1, still I cannot fix the remaining 2. So let's have L2, but now this one is fixed. Okay, this one will be P1 comes in and L1 and L2 leave there. Okay. So this is what comes in here, and at this vertex everything is fine. L1 comes in here, L2 comes in here, P1 minus L1, L2 comes in here. Okay. So everything is determined. So eventually what you have is the following: d4 L1 over 2 pi to the 4, d4 L2 over 2 pi to the 4. Okay, this is finally what you will get. And if you are not sure how I am getting this, you go back to the initial steps and repeat it, and you will eventually end up here. Okay. So let me write down the propagators that you will get. Okay. So these are these 3 propagators, and what else? You will have to include, of course, the factors of okay, and you can try to determine what that factor would be. So this is the expression for G tilde P1 P2. I am not sure I told last time, these momenta are called loop momentum. So, you have loop momenta, there are two of them, and that is why this is a two loop diagram. Okay, it is a two loop diagram. Okay. So, all good here. There is one last piece that I should settle before we can say that we have completed the this part where we wanted to write Green's functions and their Fourier transforms, and that part is, let me go back and show you. Here. So, you see, when we were writing the Green's functions, these objects, we had an integral over d tau, where the time tau was running from minus lambda 1 minus I epsilon to lambda 1 minus I epsilon, where we have to take lambda going to infinity. Okay, and H is the Hamiltonian, interacting part of the Hamiltonian, which is further an integral over the Hamiltonian density. So, there is a d cube z here, and then called tau as z naught. So, you have basically d 4 z, that is what the notation that we have used, but the time component z naught runs from minus lambda 1 minus epsilon to this. These are imaginary numbers, not real numbers. Okay, but all the calculations that we have done later, and we have been doing lots of Fourier transforms, in all those places we have been pretending as if it is usual Fourier transform, where the integrals run from minus infinity to plus infinity, okay, without paying attention to the fact that the limits were actually from minus lambda 1 minus epsilon to lambda 1 minus epsilon. And then I should argue, or should show that all my manipulations of Fourier transforms are justified, even though I had such the integral over x or integral over z was running over complex values. Okay, so that is what we want to settle now. So, we had like this dz naught, what was tau I was showing, I am writing as dz naught, and it was running from minus lambda 1 minus I epsilon to lambda 1 minus I epsilon, and then of course, we had to take lambda going to infinity, and eventually at the end epsilon going to 0. Okay. This is what we had, and we have been encountering integrals of this form. Okay, because we have been having e to the minus I k dot z when you are taking Fourier transforms, or when you are doing integrals over the internal vertices, and then when you are doing the integrals which involve these pieces coming from the propagators. Maybe I can try to show you if it is. So, somewhere here, yeah, for example, here you see we had these factors coming in. Okay, maybe further still, yeah, this one. So, you had z1 z2 here, and you have to integrate over these points, and the time component of z1 runs from minus lambda 1 minus epsilon to lambda 1 minus epsilon. Okay, and you see that you have such factors here. So, where k1, k2 and all these are coming from, and k4 and k5, k6, they are all coming from here, these propagators. Okay. And here we have been using the formulae like this. So, we wrote this as a delta function, as if we were just doing Fourier transform of the exponential, but now we realize that that is not something obvious that this should work out, because the limits are not from minus infinity to plus infinity. Okay. So, let us see why this is justified. So, we have objects like this, and of course, you have some other functions which are multiplying here, and I will ignore them right now. They do not disturb the argument. Now, clearly this is not the usual expression for a Fourier transform, okay, because a usual expression will be involving this. Right? This is what you will have if you are doing usual Fourier transforms. So, let us try to arrange for this, and that is not difficult because I can change the variables from z naught to z tilde naught, where I define z naught to be 1 minus I epsilon times z tilde naught, okay, and I say z tilde naught is real. Okay, if I do so, then I get integral dz naught becomes 1 minus I epsilon d z tilde z naught, okay. And now my integration limits run from minus infinity to plus infinity, but the exponent changes. So, it becomes e to the minus I k 0 1 minus I epsilon z tilde naught. Okay. So, again this is not looking like your Fourier transform, but at least the integration limits are okay, but here these are not real objects. So, now what I can do is I can define k naught to be 1 minus I epsilon times 1 plus I epsilon times k tilde naught. Okay. So, if I do so, then k naught times 1 minus epsilon, because when I take the inverse and when I multiply inverse of 1 plus epsilon on both sides. So, inverse of 1 plus epsilon is 1 minus epsilon, and because 1 minus epsilon times 1 plus epsilon gives you 1 plus order epsilon square term. Okay, and we are working to order epsilon, so this can be dropped. So, k naught times 1 minus epsilon becomes k tilde naught. So, this becomes with this definition. So, I will not worry about this part, because there you can easily take the epsilon going to 0 limit without any difficulty. So, I get this e to the minus I k tilde naught z tilde naught, where both k tilde naught and z tilde naught are real. So, here I have defined k tilde naught to be real. Okay, now, this clearly looks like expression for Fourier transform with whatever function you have here, you will be Fourier transforming that. This is good, but then this requires that k not be imaginary. Okay. So, if I am doing a Fourier transform and that Fourier transform involves an integral over k tilde naught. So, there you will have integral k tilde naught, okay, and this one will be running from minus infinity to plus infinity when you are doing some Fourier transforms, okay, and which will mean that when this is running from minus infinity to plus infinity, your k naught will be running from minus infinity 1 plus I just a second, is that okay? Yeah, it will be k naught will be running from minus infinity 1 plus epsilon to plus infinity 1 plus epsilon. Correct. So, this is something we should arrange whenever we are doing. I mean, this is the implication of making this change of variable. Okay, so now you have fixed the Fourier transform, but this implies that wherever k naught integral is involved, the limit should run in this fashion. Okay. Now let us see, so that is the requirement, and I should ensure this, and if I can ensure this all the time I am doing integrals over k naught, then all is good. Now we recall something, that when we were doing integrals over k naught, so let us go to k naught space. Okay. So when we were doing integrals over of integrals coming from the Feynman propagators, okay, there we saw that the poles were like this. Remember, the poles were on because of the Feynman prescription, the poles were slightly shifted off the axis, and this is what I am indicating right now. Okay. Or if you keep the poles there, you are basically integrating over this line. So whichever way you see, either you shift the poles or you say that I am tilting the axis of integration. So even initially the contour integral was the contour of integration was real axis, okay, but then we put the I epsilon prescription, which is equivalent to saying that either you shift the poles or you tilt the contour. So this contour, so let us say we are doing integral over this contour, and you see that for real parts, so this is just each k naught has been shifted by a positive imaginary part. So it is k naught 1 plus epsilon, right. So what was k naught here has been shifted to k naught 1 plus epsilon, and similarly what was some negative number here has been shifted to negative imaginary part. So if k naught is negative, so let us look at this 1 plus epsilon. If this number is negative, then this times epsilon is going to give you a negative imaginary part. So which is exactly what is happening. So you see that the Feynman prescription that we have been using has precisely done this, that it has tilted the k naught axis, the k naught contours along this imaginary in the complex plane according to this. Okay. So it has given each k naught a imaginary piece, and this is precisely what we are asking here, that the k naught integrals should run from minus infinity 1 plus epsilon to infinity 1 plus epsilon, and which is what Feynman integral has been doing, the Feynman prescription. Okay. Which means that if I completely forget about these issues here and just replace the z naughts by real numbers and integrate over real axis, I don't have to bother, because the requirement that contour integration should be like this is automatically arranged by the Feynman prescription. Okay. So I am justified in doing all the manipulations which I did involving Fourier transforms precisely for this reason. Okay. So that part is settled. Now there is only one piece which is left, and that I should discuss about is, maybe I will show you. Yeah, here. So till now I have always been talking about the numerator. I have never talked about the denominator. So next thing which we will do is look at the denominators, and then this will complete our discussion on the Green's functions, at least whatever I plan to talk in this course. Okay. So in the next video, let us start looking at the denominator.